Okay, so today is week 3 of the DIPPER Lab IoT and hardware training. And so let's get started. So as I told you guys earlier on the WhatsApp page, we are now come to start from the start and take you guys through every section into detail. So Chase started with you guys. He did schematics, how to put symbols together and route them. I think he took you through the DRCs. He took you through symbols. He couldn't take you through everything. No one can take you through everything. We can, or the best we can do is just show you a few things and how to do basic things. And as you go, you get better on your own. And then when he was done, he was supposed to, okay, let's say he did. I did, but let's say he did. So he also took you through the PCB route and how to create tracks, how to size your board. That is how to determine the size of your board with the edge cuts. I hope you guys remember all of those. We didn't meet last week because of the mid semester. I believe it went well. And since you guys are done, we can continue. So we have 4 meetings left, including this one. Okay, so today we are coming to start, as I said, from the start, and we are coming to start with schematic capture. We are coming to start with the they call it's called schematic capture, but you can call it schematic design, whatever you want to call it. Okay, so in order to like really do something, I want us to like sort of do a project. Okay, so um, we want to design something. Let's decide what we want to design. Let's specify all the components and then we'll put them together. Um, I'm assuming that some of you have had experience in Arduino and other hardware. Some of you, and those who haven't, you would still be able to follow along. You'll be able to follow along. You'll be fine. As you go, you'll be able to learn the stuff. So yeah. So because it's an IoT training session, we have to somehow use something that is going to be able to connect to the internet. And my go-to device is the ESP32. All right. So we are going to do a project around the ESP32. It should be a project that somehow sends some data to the internet. So from my experience, you can look at smart weather stations. You can look at air quality data loggers. You can look at maybe a tracking device, something that collects data and sends data. All right. And the ESP32 is not the only thing we can use. There are other stuff too we can use. There is LoRa. There's LoRa. There is MQTT. There is GSM, mobile networks, many communication protocols. But the easiest one, and for starters, is the ESP32. And the ESP32 uses Wi-Fi. From experience, once again, it's easier than the rest. So that's what we'll start with. All right. So I mentioned that to make it simple for you guys, we would use them. Jay, did you read the messages in the group? We've tasked you. So the for the training, instead of ordering PCBs from GLC PCB, for those who can order it, we will let them order it. But for those who cannot order it, like because of the cost and stuff, we'll do the CNC, but they will have to buy the copper clad, and you can facilitate that. Okay. Yeah, so he has agreed. So let me just show you the CNC machine in the lab that we use. Okay. Okay. I hope you guys can see. I hope you guys can see the feed. I can see it on the Google Meet, so I believe you guys can see it. All right. So that's the CNC machine over there. Yeah. So this is the CNC machine. This is how it looks. The PCB was recently done, and this is how the PCB looks. Yeah. So the copper clad you buy will determine the kind of layers you can route. So this one, all right, is a single layer copper clad. You can see there's copper on the front layer. At the back, there's no copper. Jay, is there any double layer copper clad?
But I haven't been eating
How about this? Okay. But there was one that we peeled.
I peeled only the front part. I didn't peel the back part. That's
Okay.
when we found out that it was double layer.
Yeah, and then this one is the double layer copper clad. So there's copper on the front. If you peel this thing, this blue thing, there'll be another layer. So with this, you can do two layer routing. Okay. So I want to make it flexible. I want to make it flexible. I want to make everything flexible. We will do the project, all right. I'll take you through everything, but you will do your design yourself. You will do your routing yourself, and if you can afford a double layer, then you do two layer routing. If you can, yeah. So if you can afford the two layer copper clad, then you do the two layer routing. If you can afford the single layer, you do the single layer routing. Or if you can even afford to ship it from GLC PCB or any of the other PCB manufacturers, you can do four layers. How many ever you can do, right? So I'll just do a simple design. I'll do a simple schematic and a simple routing so that even those who choose the single layer can still do their routing. Okay, so it's going to be very flexible. You do your first PCB, maybe single layer. Your next project you can do double layer. And as you increase, as you keep cranking it up a bit, you realize that you are learning more stuff. That's how I learned. I learned single layer first, then I moved to double layer. And I was like, oh, let me add more stuff. When I added more stuff, I had to route more traces. And single layer, double layer wasn't enough. I had to move to four layers. So with these kinds of skills, it's sort of you learn by doing. Someone has to help you start, but you just learn by doing. Okay. So without much ado, let's get into what we have to do today. So this site, Oku Electronics is going to be one of your best friends. That's where you can get some stuff, some things you can't get from here. That's where she would be able to help you guys. That's procurement if you can't get your stuff here. So over here, let's look for an ESP32. Once again, you guys doing the PCB itself is not compulsory. I know that cost is a major barrier. I was there before. There were times I couldn't afford some of these stuff. But for some of you, you guys can afford it. So uh, depending on your situation, just do what you can do. That's what I'll say. So ESP32, right? This is an ESP32 development board. The main part of it is this. Let me open ESP32 module. Yep. So right here is what we're looking at. The main part is this. This is the module. And even in the module is another main part, which is they call it the SOC. And that is this. So this is in the module. Module is on the board. You get it? For beginners, you start with board. Um, I would go through the module briefly, but for beginners, we have to start with the board. Okay. When you increase in skill, you'll be able to include the module and then you'll be able to route it. But for now, we will start with the board. I hope that's all right. Good. And by the way, over here, there isn't any ESP32 module unless you buy it externally. Actually, I think we should go with the module. Yes. Buying the module is cheaper. We would arrange all of that, okay? So, but buying the module is cheaper. Unfortunately, this thing takes a lot of space, and that's further going to make printing your PCBs more expensive. So we would rather use the module. I'll take you through everything so you guys don't have to worry. Okay, so at this point, I want you all to unmute yourselves and let's discuss what we are going to add to the ESP32, what project we want to do. Okay, so I'm listening. What ideas do you guys have? Is someone speaking?
Hello.
Yeah, Aram. Yeah, I can hear you. Could you please either increase your microphone volume or come closer to the mic? It's hard to hear.
Hello. Is it better now?
Pardon?
Hello. Is it better now?
Yes, it's better. I can hear you.
Okay. I was thinking of monitoring. Say you have a fish farm and you want to monitor the water quality so that you can change. And when the water is bad or when like it's time to change the water, your sensors will alert you that you have this quality of water, so it's time to change. Yeah, something like that.
Okay, something like that. Okay.
Or if you can also add, yeah, if you can also add like the functionality to also maybe open some tap somewhere for the water to change or something. Yeah.
Okay. So for a system like that, what sensors do you think we would need? What
Um,
actuators? Like, what are the stuff we will need?
for the sensing of the water quality, I think a water quality sensor. I've not really explored what sensors are available for that, but maybe there's a water quality sensor, something like that.
Okay, so from browsing Oku electronic sites, there's only one water quality sensor in that sense that I know, and it is this one, stability sensor. Okay, let me
Okay.
just go through to the last page and see if there's any other. Maybe he has added some. Okay, this is just liquid level sensor. That isn't a quality sensor. And then yeah, and then we have temperature. So there's temperature sensor. There is also turbidity sensor. The turbidity sensor simply measures the quality of your water. So you've seen brown
Okay.
rivers, Galamsey polluted rivers from the news. You saw that they were
Yeah.
brown. Yeah, so this sensor would measure
Yeah.
the, in quotes, dirtiness of water. You get it?
Okay.
Yep. So so what do you guys say? Should we go with the turbidity sensor? Should you go with the water quality monitoring system and use a turbidity sensor? I mean, once again, you guys don't have to implement what you do first of all, and even if you plan to implement, you don't have to use the sensors we use. This is just for us to go through it so that everyone is on the same page. So even if Aram uses this, you can use something else. Maybe Aram can buy 5 of these. That's fine. Perhaps you can't buy that. You can buy something else. There are many sensors on this page. So you just go through, see what would fit what you want to do, and then you do it. Okay. There was one I saw back here. So this is a digital barometric pressure sensor. So it measures the atmospheric pressure, and that was 28 CDs. So there are different sensors, right? So I'll go with since that's the only suggestion, I'll go with the water quality.
What about another suggestion? Another suggestion, like similar to the, it's also around water, but and this is for like water tanks.
Okay, sure.
So yeah, you have a water tank and you want to monitor the level of water in the tanks. So when the level of water is low, you then again you pump water, or you can just alert someone. You just want to alert the user that, oh, your water is low, or maybe your water is this, like at every point in time you should know the amount of water in the tank first of all. When it's low, you can get an alert, and when it's full, you can get an alert. Yeah.
Yeah, nice idea. In fact, that is one project I've worked on for a competition some 2, 3 years ago. I was measuring
Okay.
the water quality plus the level.
Okay.
Say you have a tank in your house, you never see the water in the tank. So you want to know the clarity of it, and then you also want to know the level it's at. So that should you turn on the pipe from maybe Ghana water to fill it, uh, so I automated the whole system actually. Yeah, so I included a water pump together with it. So for the water level, I think there's a sensor here. So no, this is rain detection. This is waterproof distance measuring ultrasonic sensor. So this is actually a level. This is not the one I used per se. I used an actual ultrasonic sensor. I use this ultrasonic sensor. It's a distance measuring sensor, but it's not waterproof. There is a waterproof version. And finally, there is the actual liquid level sensor. I think this recently came. It was not available when I was doing my project. So let's look at two things. Let's look at two things for these two sensors. 119, 199. Let me add the ultrasonic sensor. So one thing you'd realize with these two is that they have 4 pin connectors. The ultrasonic sensor has 4. The waterproof ultrasonic sensor too has 4 pins. You look at the package or the breakout board. This is the board, and then the ultrasonic part connects via wire to the back here. Okay, so this has 4. This too has 4. But this guy, looking at it, I think it's 3. There is 4. This is a 4-pin connector from the actual or the actual level sensor. And then this connector looks like 3. I can't really see, but it wouldn't be bad to size for 4 actually. So if you just use 4 connectors, it wouldn't be bad. No, so it's a 3 pin connector. I know this thing doesn't make sense, but from experience, that's 3P over here. That's 3 pin. Yeah, so this is 4 pin, and then this side is 3 pin. So we would do we would assume that we would use this. Let's assume that we would use this. So the parts, right? ESP32 module. That's number one. And then we are going to use, let me copy it. Okay. And then, Aram, you also mentioned the stability sensor module, right?
Yes.
Okay. Okay. So with these, just the ultrasonic sensor module and the stability sensor module, we can transmit some data, right?
Yeah.
Okay. So let's design a let's add a pump. Okay. Yeah, let's add a pump. So you come here, pump. There are various types. The two the two compatible ones are this one and this one. This and this. And to make this lesson challenging, I'll go with this one. Yeah, and you see why. So I'll go with this guy. Okay. All right. So we have our stuff ready. Now let's build sort of a flow diagram or flow chart, like how we are going to connect everything. Okay. So
So
can you guys
can
hear
you
me?
guys hear me?
Aaron.
Aaron.
Yeah. I can hear you.
Okay, so we are going to plan our system. I wanted to use flowchart, but it would just make things lengthy. Writing is easier. Okay, so what were our sensors? We had I think we had an ultrasonic. We had an ultrasonic sensor. Okay, that one will be fed inside here. Then we had the level sensor. No, wait, sorry. Okay, so we have the ESP32, the ultrasonic sensor, the stability sensor. I made this mistake. Yeah, so it's five, not four. Okay, so this is how our system is supposed to be like. So we have inputs, ultrasonic and stability, and we have outputs, pump. This is just a simple block diagram, but this is not going to get things done. Okay, because we have to look at things like communication protocols. Um, that's how maybe the ultrasonic sensor is going to send its data to the ESP32, or how the turbidity is sending its data to the ESP32. We also have to look at um, power requirements. So for the ultrasonic sensor, what voltage level does it require? Or for the turbidity sensor, what voltage level does it require? Okay, and then the same for the pump, all right? So it's actually two main things: power requirements. That is what everyone is getting in order to come on. Okay, ultrasonic turbidity pump and even the ESP32. And then we have, I can't write well because of this thing. Okay, but I think you guys can see it. If I turn it, how shall I turn it? Yeah, I think this is better. Okay. Yeah, and then communication or compatibility. That is, can this talk to the ESP32? If it can, how is it supposed to do it? Same for the ultrasonic sensor, same for the ESP32 to the pump. And even within this, we have to look at voltage levels. When we get to the schematic side, we would consider all of those, all right? I think we can do the schematic in one day. So maybe I'll use today to look at all the requirements, do all the plans. Okay. So we take that off. Now let's go back to the Oku electronics site. So I have left everything that we need open. The pump, the turbidity, and the two ultrasonic sensors. Okay. So you see, let me bring this back in. So in our system, the main component, usually when you are doing a PCB or a system or any project involving these kinds of electronics, there will be a main component, and for us, that's the ESP32. Okay, because it is connecting to everything in the system. It's taking data from the two sensors and it's giving commands to the pump. All right, so it's basically the brain or the heart of our system, and usually that's the first thing you should look at. Okay, so I come to this site. This site is Expressive. They are the manufacturers of the ESP32 SoCs and the modules. They even make some boards. So quickly, we go to hardwares. You see the SoCs, as I mentioned. We see modules. We see dev kits, which are the boards. Let's go to modules. And now, for beginners, this can be very confusing because when you come here, there are so many modules. Okay, You can continue scrolling, continue scrolling. There are a lot. Okay. So to make things simple for you, this is personal advice. You can take it or leave it, or you can go your own way. But from experience, this is personal advice. The so number one, for beginners, I would recommend going with so you scroll, come to this section, ESP32 series. I would recommend in any project you are doing, right? So many of them. For the ones that have end of life, don't even look at them. For the ones which say not recommended for new design, that one don't look at them. But look at this. Okay. So you see, they have series. Let's go back to the top. So for example, we have the S3 series. You come and there are different kinds of modules. I will touch on their differences briefly. Then we come to the S2 series. You also have your modules. Then you continue C series and so on. Okay, the thing is that every series has different kinds of capabilities. For example, there's this series, the P series. It's not here yet because they have no main modules for it. It's just an SoC that is there. But for the P series SoC, I don't know, let's take a look at it so that I know what I'm saying. Yes, the P series SoCs, they don't have Wi-Fi. They don't have Wi-Fi. Let's look here. So the S3 series, where does it say that it has Wi-Fi? So it says in the description, it says generic Wi-Fi. One thing too is that it will be hard to find information, but as I said, the longer or the more as you use the site more often, you know where to find stuff. It's not like I just knew. I had to come here often. So generic Wi-Fi plus Bluetooth. So this thing too has Bluetooth. Okay. So this one has Wi-Fi and Bluetooth. In this one's description, it doesn't have Wi-Fi. I can't see the description here. But then again, in the S3 series, they've written it here. Over here, it's not written. The reason is that they had to make some trade-offs. So this series is more geared towards maybe if you are making interfaces like LCDs or displays. You see the small devices that you meet at the cashier when you go to a mall and you go to the cashier. Those POS devices, they can be made with a microcontroller and it has a screen. Okay, so you have to, because someone is interacting with the screen, it has to be fast. So they've made this specifically for POS devices. Okay, stuff that display graphics. So I think they had to remove the Wi-Fi. But for the other series, they are slower but have Wi-Fi. So that's just the differences in series. You have to, if you want to, read all the series and know their differences. But for beginners, as I said, I will recommend this module, ESP32 Room 32E. Some people call it Room. Why do I recommend that? I recommend it because if you are to buy any module, that's what is on it. That's very common. It was one of the good modules that came out and it came to stay. Okay, so if you come to Oku Electronics and you click on this, it should have the ESP32 room module. It's not stated here, but I know it does. Because when I zoom in, I can see it ESP32 room 32. Okay, the room 32 is actually duplicated. Some 32s are duplicated, but this is the same as that. So when you buy your board from Oku Electronics, you are buying an ESP32 room 32E, And as I said, it's advisable you start from there. The next one I'll recommend is the S3 series. That's at the top. This is the most powerful series out there, and it's not even that expensive. Um, I think this is $4 or so. 32, the room 32E should be like $3 or so. But this one is the most powerful, except for the P series. This is the most powerful currently, and it has more functionalities. It's like I can't explain it because I'm still using it currently, but it has so many features compared to the 32E, which is best for beginners. So those are the two I recommend, and those are the two I've used in my life. I can't recommend other ones because I've not used them. Okay, I've used this one before. So this one is just the room 32 1U. Room 32, sorry, room 1, room 1U. The difference between the two is that this has an external connector for an antenna. This module, right, if you look, let me scroll in. So this module over here, this is the antenna for the Wi-Fi and the Bluetooth. Okay, it's on the module. And when we are doing routing, which Lemuel will take you through, he will tell you about the keep out area. There shouldn't be stuff near the antenna. But when you come here, there is no antenna. What you have is some kind of connector over here. And that connector is actually called a UFL connector. Let me search connector antenna. So you connect something like this. You can connect something like this to that point, or you can connect something like this. I saw another one. This one too. Okay, so yeah, for now, this is a lot to take in, considering the fact that we've not even routed anything or done any schematics. These are just some head knowledge that you should have before we start, because you should know your stuff before you can use them. You get it? Okay. So, all right. So the next thing we should get is the data sheet. I spoke about data sheets last 2 weeks. Jay has spoken about data sheets. Lem also has spoken about data sheets because they are very important. You click on this link, you get your data sheet. Your data sheet is the manual to using this thing. Worst case scenario, you don't use your data sheet or you don't know your data sheet, you end up spoiling your module. Best case scenario, your project will always work except you write wrong code. Okay, so the data sheet is a lot, 52 pages, but we will not read everything. The only things we are going to look for are, sorry, I selected the wrong module. So you are using the 32. Yeah, sorry. This one. Sorry about that. Okay. So yeah, ESP32, room 32E. So this is the first thing I recommend that we find in our data sheet. You want to find the voltage supply. Okay, you want to know the voltage, how many volts it takes. So two common voltage levels in electronics are 3.3 and 5 volts. 3.3 and 5 volts. 5 volts is for, I think, the older microcontrollers. So I have used Arduino, and the Arduino requires 5 volts. The Arduino Uno. The Arduino Uno, let me be specific. For those of you who have used the Arduino Uno, you know that it requires 5 volts. The ESP32, however, doesn't and shouldn't take 5 volts. You supply 5 volts, you will damage. You supply it 5 volts. Best case scenario, your module will become extremely hot. Worst case, you will destroy it entirely. Okay. So where does it say that it requires 3 volts? Okay. So the data sheet is a lot. Over here. Yeah. So you're actually given a range 3.0 to 3.6. This is the range of voltage that you can supply to it and it will be okay. You can see that you can't go above 3.6, you can't go to 5. So why 3.3? 3.3 is a standard voltage. Why not 3.2 or 3.1? Because on the market, most of the regulators, okay, so let me look for that voltage regulator. It's called a linear and low dropout regulator. You would have to include one of those. Yeah, so specific common examples 1 volt, 3.3, 5 volts, 10 volts. You don't see 3.5, you don't see 3.6. Okay, even though if you had the skills, you can get 3.5, 3.6 for fixed regulators or for standard voltages. You just go with 3.3. 3.3 is in the range, so you use that, you should be okay. Alright. So for the ESP32, we write that we need 3.3 volts. At this point, I will not use the data sheet anymore so that things can go fast. With your own time, you can go through the data sheet and see what you need to do. But I'll just give you the do's and don'ts. Okay. So the first do, use 3.3 volts. Second do, the inputs, the sensors, they shouldn't supply 5 volts. They shouldn't supply the more than 3.6 volts. Okay. So even as the power range is 3.0 to 3.6, it also means that you can't supply more than 3.6 to any of the pins on it. Okay. And that's important because this guy is 5 volts. This guy takes 5 volts, and I'll show you very soon. I think this guy too takes 5 volts. So we'll see how to connect the ultrasonic sensor to the ESP32, even though they have different voltage ranges. We'll do that. Okay. Alright. I think the next thing we should look for is so I mentioned that there is this that you should always come to application section. Okay, it's called module schematics. No, peripheral schematics rather. Yeah, peripheral schematics. What do we want over here? Over here, they will give you the recommended connection. The recommended connection in quotes. So let me open another data sheet out there. Okay, I'll open this one because I've recently used it. Yep. So this part is a battery charger IC. I recently used this in one of my designs, and this one too is quite a lot. So I come here and I go straight to application and implementation. Sometimes I first come to specifications, electrical characteristics. Some of them will tell you their input voltages, but because this works differently, there isn't any input voltage per se. You look through here, there's nothing like input voltage. Over here, you see input power detection threshold. Let me just go to the application section. Okay, so application information. This is where they give you recommended connection diagrams. Okay, so this is your IC. They tell you that you should use an LED and resistor over here to an LED and resistor connection. Over here, you should connect your adapter. Like they tell you, and then some calculations you should do depending on the part you're using. Once again, this is a complex IC. We wouldn't be using this for now. For those of you who would continue to do PCB design, you get this soon. I was once where you are, and I've gotten here. So you just continue learning and get there too. So for this, there, I would say the two things that we need is this. This is the reset configuration circuit. I will touch on that soon. And this is the boot selection. Let me add this to it. This is the UART connection. So we are going to copy three things here. We are going to copy 1, 2, and 3. Why not the others? Because the others, we will not use them. JTAG is for debugging. JTAG is for debugging. We will not get into debugging, so we don't have to do this connection. And then this over here. So we have to do this. This is the recommended filtering capacitors for the 3.3 volt supply. In electronics and PCB design, you would hardly see 3.3 volts, rather you see 3V3. It's the same as 3.3. If you see 5K1, let me write that here. So 5V5, that's 5 volts. Resistors, instead of 5.1 kilo ohm, what you would sometimes see is 5K1. Okay, so don't get confused. The K in the middle is just sort of like the decimal. So 5 kilo ohms dot 1. Okay, I hope you all get it. I'm trying to figure out what this is. IU32 and 33. Okay, this is a crystal oscillator. We wouldn't need this. So the things we will need is this filtering capacitor network. We will need this is the reset button. We will need this, the boot selector. And then finally we will need this. So this helps us to program it UART. That's how we are going to program the ESP32. The boot selector, there are two modes in the ESP32. You are either programming it or it is running normally. So when it's time to program it, you would have to do something over here. Then when you are done, you have to do something again here. This is reset. You click it, you restart the whole system. So when you open keycard, if you have never done any project, here should be empty because this is the last project I did. Sorry. Because this is the last project I did, that's what is showing. So you'd go to new project. I think we have to start schematics today. We have to. So let me, I think I'll do it in my documents. Keycard. Let's call it okay. And then I would uncheck this because I've already created a folder. Then you put the name of the projects to here. So it's either you don't create the folder and you just put the name here and click save, or you create a folder and check this, put the name here, click save. And when you are done, you should get this. So you have a lot of stuff over here. Two main stuff you should worry about for now is just schematic editor and PCB editor. The rest, as I said, will come to you as you progress.
So I would first open the schematic editor. I think we can go ahead. So for those who started with us, I told you about how to interact here. The left mouse button is to select stuff. The middle mouse is to zoom in and out. When you press the middle mouse button, you actually drag around, and well, actually you can use the right too for dragging, but I'm so used to the middle mouse button. So middle mouse button and right mouse button drags the page around. And as I said, you would want to use a mouse. Like if you use a touchpad for this kind of software, you would really stress yourself. So probably you should get a mouse and use it when you are doing this. Okay, so you want to add stuff. Click here, and then we search for ESP32. So this will take a while. Loading footprint. It's reading all the data we have, all the footprints available, and it's compiling them. This shouldn't happen every time. For example, I close it and I come here again and it pops up. Okay, so it's just a one-time thing. So ESP32, room 32E. So you come here and there are a lot of modules, a lot. We have this one. I wouldn't use this library, PCM Expressive, because this symbol is a little bit messed up to me. This one looks neater. Okay. So I have to use one of these. What did we select again? We selected the 32E. The 32E. So 32E. That's here. Alright. So you just double click it. You drag it to your page. You click. And there's still another one. It's still there in case you want to put two. So maybe something like resistors. You're putting resistors. You're going to put like 10. You don't want to go in there every time and click and click and click and click. So this is a feature. You click, it's still there. If you want to, you can put as many as you want there, but we don't need to. Okay, so we just need one. Okay, so when you place it there, you just press escape and it should go. Okay, if this comes, you just press escape and it goes. Okay, so we have our module here, and we have our pins out here. So let me open this one on the side. Let me snap it here, snap this here. Reduce here. I have to do some tweaking and reduce this one too. Okay, let me increase this one a bit and we can see everything. Okay, so the first thing you want to do is the capacitor connection. The capacitor connection. So that is connected to the 3v3. 3v3 is pin 2. We don't see 3v3 right here, but we see pin 2 here and it's labeled VDD, and VDD is still 3v3. I'm sorry for some things that I say, you may not be able to relate to it, but that's because I've come quite far. There are some things I'll just say without explaining, but just bear with me. So all I'm saying is that 3v3 is the same as VDD. And for those of you who are students, you've seen VDD before in electronics courses, computer engineering, electrical engineering. Okay, so our connection is going to be over here. So there are two things required for our connection to 3v3. That is this capacitor and this 22 UF and 0.1 UF. These capacitors are called decoupling capacitors, decoupling and filtering capacitors. I think the 0.1 is for filtering and the 22 is for decoupling. Okay, so what they do is that your power supply could be noisy. Instead of it supplying a constant 3.3 volts, you could get ripples. Electrical engineers, I did electrical, so I know that the electrical students here, or at least some of you know about ripple voltage or the noise, like noise in voltage supply. Okay, so the 0.1 UF capacitor or 100 nanofarad capacitor, the same value. Okay, what it does is that it filters out the high frequency components in your voltage signal. So it's going to do its best to give you a constant 3.3 volt supply. So that's what the 0.1 UF does. If you actually do the calculations with the frequency, I think this formula, uh, the xc, that is the reactance of a capacitor, is equal to 1 over 2 pi fc, and some other formulas. Those of you who are like, you guys are students, so you guys will remember these values. You use those formulas and stuff, and you'll be able to find out that for a very low capacitance like this, you're actually filtering out high frequency noise. If you were to use this big capacitor, um, you'd either be filtering out, I think you would rather see, never mind. So all I'm saying is that these values are not chosen as random. Okay, 0.1 UF is for filtering out high frequency ripple noise. 22 UF is not for filtering per se, but it's for acting like a reservoir. Okay, so as the voltage is as it's changing, or they are transient, maybe at one time there could be a spike, it could jump to 5 volts, and within 3 milliseconds it's back to 3.3 volts, or it could dip and then to come back up. The bulk capacitor, what it does is that it tries to maintain the voltage. So when the voltage increases, the capacitor has to charge up, so it's not going to change its voltage much. All right, or when the voltage reduces, there's charging the capacitor, and it would supply the ESP32 for some time until the voltage comes up to charge it back. All right, I know we are here to do connections, but I think the descriptions are very important. So that is why we are using these two values, 22 UF and 0.1 UF. You could use 20 UF or you could use 0.2 UF, like any different values in some range. I think the range is in the electrical specifications, but because it's given to us, like they've just told us in the recommended connection that use this, I think we should just use that. Okay, so how do I add capacitors? Once again, I prefer not to click, so I would rather use the shortcut A. You mouse over here, you see A in the bracket, that's the keyboard shortcut, so you just press A and this comes up. Search capacitor, scroll down here, see device. You can see a lot of capacitors. There are a lot, but one of them that you use a lot is this C or C small. Sorry, either C or C small. We have CUS. It just has this curvature, and then CUS small. I mostly use this in all my designs. It's just this that I have used. Um, so let's quickly search Oku Electronics for something. Okay. So you come to Oku Electronics and you can see different types of capacitors. Two common ones are called the electrolytic capacitor and the ceramic capacitor. The key difference is that for electrolytic capacitors, polarity matters. Okay, you have to connect positive of your supply to a specific pin, which is usually the long pin, and negative of your supply to the negative pin, which is usually the short pin. For ceramic capacitors, it usually doesn't matter. Like most of the time it usually doesn't matter. So which one should we go for? So for the 0.1 UF, the ceramic capacitors will do. Okay. Most of the electrolytic capacitors are bulk capacitors. Maybe this is 1 UF, that's the lowest I've seen. Okay, there's 100 UF capacitor. But then, as I said, we are trying to do filtering, not bulk supply. So it's ceramic that we'll go for. And let me just show you this. MLCCs, multi-layer ceramic capacitors. In my designs, these are the ones I use. These are the SMD equivalents of these ones. Okay, these ones you have to drill holes into your board and push them through, and they are big. But these ones are very, very small. The smallest one you can fit like 10 on your thumb, and they take up less space. But you see, because of how we are going to do our board, we are going to print it out ourselves, and we are going to solder the parts. These parts are hard to solder, the SMD parts. If they are big, they are hard to solder. If they are small, you can't solder them. So we would go with through hole. Most of our stuff are through hole except the ESP32. The ESP32, for those of you who would do the boards, will help you with the soldering. But for the rest, you will be able to do it. So let me just look for 0.1 UF capacitor. Let me change it to 100 NF. 100 NF, and I get these ones. So this one is here. This pack is 3 CDs, and I'll go with this. Okay. So for the ceramic capacitor, you just need this symbol. I'll place this here. I'll press X to mirror it. Press X to mirror it, Y to mirror it up and down, and then X to mirror it left and right. I use a lot of keyboard shortcuts, so as I said, this didn't mirror X. So this is our 100 NF, and you have to change the value. Okay, so anytime you place your symbols, there are two stuff you see. You see what we call the reference. The reference is usually never changed until we are done, and value is like so for resistors, capacitors, you put in like whether it's 100K resistor or 100 NF capacitor. For ICs and stuff, it's just the name. So I have to change here to 100N. Okay, 100N. And then we need a 22 UF capacitor. So I don't have to check. I'm sure there is one. But we have to check. For every component you're going to use, you have to make sure it's out there. You have a way to buy it. Wow. Okay. We have 22 UF capacitors and they are in stock. So we just add it. So polarized. As I said, the electrolytic capacitors are polarized. You click on the symbol, you can see that there's a pin labeled plus, alright? So you select that X and put it there. I don't know why when I press X, it turns, but when I place it, it doesn't turn. And you change your symbol to 22U. You don't have to add the F. You really don't have to add the F. You usually never have to add the F. For resistors too, you just put whether 2K or 22K. If it's 2 ohms, you either do 2R. When we get there, I'll show you. When we get there, I'll show you. Okay, so we have this part set up. What is this part? Let's connect our stuff before we continue. So you either click here or you press W. Sorry. So connect this, then connect this part. Now we have to connect this part to ground. You can either do this, which is messy, or you can use the ground symbol. Now this is where I have to include the power symbols. So under place symbols, we have place power symbols. Okay. Right. Wow, it's almost 6 o'clock. Let's make it like 6:10, 6:20. Okay. So right now I'm looking for two things. My 3.3 volt power symbol and my ground power symbol. So we have 3.3 over here, or you can search for it over here. But I was able to pick it out. I saw it. So this you place here. Escape. You can place it anywhere, but it should be here. So what this simply means is that whatever you connect, you can duplicate this and come and put it here. And then you would connect here to here. What it means is that in your routing, you would have to route power into this pin and power into this pin. Okay. You see, there's a way that you should do your schematic design such that um okay. Aram says I should go through the 3.3 volts again. Can you kindly go over the 3.3 volt symbol again? Okay, so that's what I'm touching on. So let me switch to my camera over here. Okay, yeah. So let me draw something. Let's say that you have a battery supply. Let's say you have a battery cell, and this is 1.5 volts. This is plus, this is minus, and you want to. Yeah, Aram.
Okay.
Hello.
I was asking how you'd add the symbol, like how you add the symbol to the drawing, like where you go to find the
How I add it.
3.2. Yeah,
Okay, but you understand how it works.
yeah.
Okay, but for those who might not, let me just go over it briefly. So let's say you have bulbs, three bulbs, you want to supply 5 volts to them. In your physical connection, you do it like this, like this, like this, right? And then you bring them here, here, and here. We don't have to draw things like this in schematic. What you'd rather do is that you first bring your bulbs. You know your bulbs require 3 volts. So you use a symbol. This is what it looks like, 1.5. And then you rather connect it here, then connect it here, then connect it here. Then we have ground, connect it here, connect it here, connect it here. Then somewhere out there, you would put your battery. Then you put the symbol there again, and then you put the ground there again. So what it means is that whatever is connected at the symbol is connected together. So this is connected here, and this is connected here. You get it? That's what symbols are. All right. So it will help us make the schematic nicer. We don't have to put wires everywhere. Okay. So the power symbol, I said you come here, place power symbols. You click here and you have your power symbols over here. So you can either scroll through and search, or you just type it here, 3.3 volts. And we have plus 3.3 volts. We have other 3 volts, but for simplicity, I don't really know what the others are. I think in complex power circuits, you would need these ones. So is this what I selected, 3.3 volts, and I placed that there. All right. The next I need is ground. Ground is ground. So you can see that over here, their ground symbol looks different. What you could do is that you could go for any of the other grounds. You could go for this or you could go for this. As I said once again, it's just symbols. When you bring this, you can come here. Can come here and change this to ground if you want. But I don't want to do that. I just want to use what's over there. So I'll use the ground. I know it looks different, but it will still work. So ground to ground. And then I'll do Control D. Right click. Duplicate is Control D. So Control D to duplicate, and then I bring it here. Simple as that. Okay. So let me drag this up a bit so that a wire can pass here. Let me bring this down a bit. You don't have to do this. I'm just trying to make my schematic more compact. Okay. So we are done with this section. The next section is, so we have to do this too. See whether I have to explain this because it could be complex, but some of you may not get it. But let me just explain it. Okay. So this right here is called, I think they call it the boot control. It's mode control. No, not this one. Okay, so it's actually in the data sheet. This part of it. I think it's rather reset. Then it's not this one, it's actually in there. I mean I have to show it to you guys, so you know what, never mind. So that circuit over there, this circuit is called an RC filter circuit. Okay, let me redraw it so that you can see how it actually looks like. An RC filter circuit is something like this. So we have a capacitor. Trying to remember how exactly it looks like. Yes. Okay, this is an RC filter circuit. We have a resistor in series with a capacitor. So what does this kind of circuit do, and why is it in the ESP32 schematic? This is what it does. So imagine let's say you flip a switch. At that moment, the voltage that was going to the ESP32 changes to 3.3 volts in an instant. Like, so the ESP32 senses the voltage and it comes on. However, we don't want it to be so fast. We don't really want it to be so fast because it has to do with power supply and noise and stuff. Okay, so you want a way to slow it down. You want a way for when the power is switched on, instead of it quickly jumping to 3 volts, it rather, instead of, let's say, it goes and then jumps, you want it to rather come and then do something like this. You get it? So that's what this does. Basically, that's what this does. I wouldn't go deep. So the value of the resistor and capacitor is going to determine how fast the change happens. Okay, and that is done at the EN pin. At the EN pin. Why the EN pin? The enable pin is the switch of the ESP32. The enable pin is the switch of the ESP32. So when you supply power to this and there is no voltage here, the ESP32 would not start. It wouldn't start. But when you now supply voltage at any time, as long as there's power here and you supply voltage here, then it will start. Okay, and that is what is used to reset it. Let me show you. Here, see, the EN is here. And then don't look at this capacitor for now. As I said, it's for filtering. When you see this, know it's for filtering. Most of the time, and in other times, if we ever come there, we'll see. But this is what the switch does. When you press the button, it shorts EN to ground. Shorting it to ground means that the voltage is 0. And when the voltage here is 0, it means that there's there's no voltage there, so it goes off. So when you click the button, it turns the ESP32 off and on quickly, and that's just what resets us. Okay. For the electrical students who are worried about short circuits, because we are supplying 3 volts here and then you short it to ground, wouldn't there be a short circuit? Answer is no. Why? Because of this resistor here. So let me come back here. So at this point, what we have is so this is where the switch is put. When you close the switch, where does power flow from? From 3 volts through this resistor, through this switch to ground. Due to this resistor here, which is usually 1 kilo ohm, little current flows. So there is never any short circuit when you are doing a reset. If you ever forget this resistor, yes, you are going to cause a short circuit. And if you are using a battery, your battery will get very hot. Or if you are using a charger or something, for chargers which are not protected, you could blow it up. Okay. Yeah, a lot of theory today, but we have to do it. So it is done here at the EN. So let's duplicate this. So I am going to need a capacitor. Aha, yes, the values are not stated here. So what I was looking for was over here. When I first started developing with ESP32, it took me a long time to find this, but for you guys, it's not going to be that long, luckily. Yes, hardware design guidelines. Nope, sorry, wrong one. We are here. Hardware design guidelines. So this is another documentation by Expressive. Hardware design guidelines. I don't have to explain it. Guidelines for designing a hardware around ESP32. So this is where you have to come to. Schematic checklist. Quickly, let me be fast. So everything we are doing is over here actually. They go through everything you ought to do. Power supply. So I should have actually brought this up before we started. Okay. So they are even stating that you should use 3.3 volts. But on this part, okay, this one is more complex. But then this is what we are looking for. Let me quickly.
Hello, Nathaniel.
Yeah, Aram.
Please, I'm no longer seeing your screen.
You are no longer seeing my screen. I can see it. Hello, is anyone else not able to see my screen? Because from the Google Meet here, I can see my screen. And when I drag this here, um, hello, can anyone else not see my screen? So someone replied you saying leave and join, meaning that he could see, and people are replying that they can see. Aram, are you using a phone or a laptop or something else like that? Hello, Aram.
Hello, yeah, it's working now.
Yeah, it's
Thank
working
you.
now. All right. Okay. 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 Yeah. So this is the. I'm continuing, right? This is the part where we get our values from. They said that the recommended setting for the RC delay circuit is R is 10 kilo ohm. Sorry, so it's 10 kilo ohm, not 1 kilo ohm, and C is 1 UF. Okay, that's the recommended value. You do your calculation, you will get some kind of milliseconds that it's going to delay for it to rise. It's all in the documentation. Okay. You guys, one thing about hardware is that you have to read documentation. Okay, people have made their chips and they know how it's supposed to work. If you want to successfully use it for something, you have to also read the documentation. So if you are someone who doesn't enjoy reading or struggles to read and you want to do hardware, you either have to struggle and read or maybe you have to find another hobby. But it used to be me. I used to struggle to read these stuff. So you can use me for inspiration. If you struggle to read these sorts of long documentations, don't give up. Just persevere. The only thing you should learn how to do is read what you need. You don't have to read all of this. Look at this long documentation. All I came here to do was look for this, and we are done. Okay. So I'll put this here. So they said that the resistor and the capacitor are 1 UF and 10 kilo ohm. So for resistor is here and it should be somewhere here. Okay, capacitor. So for capacitor, should we use electrolytic or ceramic? I think we should use electrolytic. So C polarized and it's dropped here. So let's align this. Let's arrange this. Let's connect this. And then let's connect this here. Okay. Remember, the plus should be up here and the ground should be here. And then 3.3 volts should be here. Connect this. Connect this. Values we're given 10K and 1U. All right. So back to our data sheet. We are done with this side. Okay. We have what? 1, 2, 3 more to go. Okay. So let's do this. Let's do this. Let's do this quickly. The reset part. We will need a switch. Okay. So to make things simple, not complicated, instead of using a switch, I'll use a jumper. I'll use a jumper. A jumper is just, you can use a header for a jumper. I'm looking for jumper and they are giving me movies. Yep, so this is how a jumper looks like. So there are two parts. This part are the header pins. You just put them there. And then there is this thing that you use to bridge two connections. Okay. So let's say I have a 2-row header and I connect one part to, let's say, oh, sorry. Hey, you guys, I did a wrong connection and no one told me. We are using EN, not this. We are using EN. So we have to drag this up and use EN. Wow. You guys, if you think I make a mistake, you can unmute and pause me. Okay. Yeah, I still make mistakes. I'm not perfect. So as I was saying, this can act like a switch. A switch simply bridges two parts. A switch bridges two parts. So instead of buying a switch or soldering a switch, we'll just use the jumpers because they are very easy to solder. Okay. So let me put jumper here. And it's going to be open. You can delete this. Sorry. Let me rather use a connector. The connector is not the one to use. So that's the jumper. Okay. Connect this here. Okay. Yep. Nah, I'm not done, but we'll finish soon. I was supposed to remove this. I hope you guys get it up to this point. Hope you guys get it up to this point. And then over here, there is a 0.1 UF capacitor. So let's add that too. We could simply duplicate this one and bring it here. You might say there is a resistor here, but this resistor's value is 0 ohms. Honestly, I don't know why there's a 0 ohm resistor here, but it's literally a short circuit. And if you research, you would find why 0 ohm resistors are used in PCB designs, but for our application, no, we don't need that. Okay, so this is connected between ground and EN. Wow, so I have to find a way and okay. So we have to move things. See how I'm struggling to make my schematic beautiful. In PCB design, in schematic creation, you always want to make sure things are done properly. Then we could just use this ground. Could just connect these ones here. Yeah, so that's basically the connection. This over here broken and brought here is just this added here. We could have broken these two away, but I see no need in this simple design. In some complex designs, yes, I have separated the switch and capacitor from the ESP32 here. But over here, we can just add it. Okay. The boot option, that one too is a header or a jumper. Sorry, that one is a jumper too. So I click here, duplicate here. And so boot is connected to IO0. You read the data sheet, it's said over there. So if you come to strapping pins, it's called a strapping pin. Okay. Let me look for where the configurations are. Right over here. So this is the chip boot control table. So this is simply saying that if you want to start the ESP32 normally, that is SPI boot mode, GPI 0, that is IO 0, should be 1. 1 means 3.3 volts connected to it, and GPIO 2 should be any value. Okay, so if you have a jumper, okay, so GPIO actually, GPIO 0, it's internally pulled up by a resistor. Pulled up by a resistor. What do I mean? This is the ESP32. This is IO0. If you take a multimeter and measure here and ground, you read 3.3 volts. Why do you read 3.3 volts? That's because deep within the ESP32, they have put a resistor there and connected it to 3 volts. So there is 3 volts through a pull-up resistor connected to the GPIO0. That's what we mean when we say it is pulled up. You've heard it before, pull-up resistor, pull-down resistor. Pull-up resistor is connecting something to high voltage or positive voltage through a resistor. Pull-down is through a resistor to ground. Okay, so at any point, if you connect nothing to GPIO 0, the default value is 1 or 3.3 volts. Okay, if you want to send it to 0, then you use the jumper to short it to ground. And that's what is happening here. Boot option. So there is the IO0 and then there is ground. You put a jumper there and you short it to ground. Once again, due to the resistor, there is no short circuit. All right. I hope that is clear. So I will move this here, connect this here, bring ground, and connect this here. And that's done. So you put a jumper there and then you've put it in joint boot download mode. So if you want to now program your ESP32, you put the jumper there, you press reset, and it will start in download mode. Then you can now, maybe if you are using an Arduino IDE, you click the upload and then it would flash to it. All right. For I know there's GPIO 2. The reason why we don't have to do any connection is that it has to be either 0 or any value, meaning it can be 0, 0. And that has no pull-up resistor, so at any point it's always 0. So we don't have to do anything for GPIO 2. Okay. And the last one is UART. UART is what we are going to use to program the ESP32. Okay. So because we have to close, let me quickly do it and then give any final thoughts or any final words and then we would close. So for that one, I would need so TXDO, RXDO. I'll need a 1x4 pin type connector. So 1x4 pin comes here. I place it. Okay. So because of how it is, I wouldn't recommend placing it directly here. What we would rather do is that Let's bring it here. Let's put it here. Okay. Then, so in the data sheet, we are to connect VDD33. For simplicity's sake, that's also 3 volts. Okay. Why it has a different name, you want to find out, you could read the data sheet, but for simplicity's sake, VDD3 is 3.3 volts and the ground. So duplicate these two. Arrange them well because we want a beautiful schematic. Connect them up. The ends are connected. And then this is where we use labels. Okay. So I'm a person who usually likes to go according to what's the name again? Standards or best practices. Yes, I like using best practices. Now I know that last 2 weeks we used these kinds of labels, global labels. So let's say RX. Let's name it RxDO, RxD0. So you put RxD0 here and you connect it, right? This is what we did last 2 weeks. But in this scope, this is not what we are supposed to do. Okay. And here is why. So in many PCB design softwares, there are two main kinds of symbols. We have global labels, that's this. And then we have net labels, which is this right here. So what's the difference really? Let me bring net label to TXD0. So a net label looks like this. Place it here. Then you connect it here. Also a label. Okay. What is the difference between these two? The difference is that when you get the level where you are doing multiple page schematics, and multiple page schematics is where you need another page. So you simply come here. No, it's not here, rather, it's rather here. Where is it again? Wow, have I forgotten where it is? I used to use this thing a lot. I should be somewhere here. I'm coming. Oh, hierarchical sheets. No, it's not this. These hierarchical label, these global labels. I think it's this. These hierarchical sheets. Yeah. Place hierarchical sheets. Wow. So let's say I do this and then I name it me and then title me. Just name both of them me. Make sure the second one ends with this extension name and you click OK. All right, what happens? You get this. It says here file me.keycard.stk and then you click here a new sheet, but it's still part of the old sheet. So now you are doing, let's say your design is quite big and it's quite big, there are lots of parts and you want to maybe uh, so from experience, I've done a design where I had to do power for 3 volts, 5 volts. I had to do another 3 volts. I had to manage a battery, my battery charger, and a lot of things. It would cloud up my one sheet. So what I'll do is that I would come here and instead of here being me, I'll name this power. And I'll do everything that's to relate to power here. And I would simply place the power labels here. When I come here, I just bring the power labels in. So if I need 3 volts, I just put it here. If I need 5 volts, I put it here. Then when I come here, this is where I define how I'm providing the 3 volts and the 5 volts. I hope you understand. So in multi-page schematics, all right, let's say you have a global symbol, you would be able to connect that global symbol here. But if you have a net label, you put TXDO here, you come and put TXDO here, the two wouldn't connect. Okay, think of it like, how should you think of it like? For those of you who have done programming, local variables, global variables, it's just like that. So global variables, you can get global pins. You can use them in any sheet. They all connect together. Local variables, you use a local net on one schematic. In the next schematic, you use it there. It doesn't connect to the previous sheet. Rather, you are creating a new label in that sheet. You get it? So I know it's a lot to take in once again, but for the sake of best practices, we would go with the net labels. So I'll delete this. I'll delete this. If it's just one page schematic, you can use the global variable and fine, it would work. I mean, in a program, a small program, you can use all global variables, it would work. But then, once again, for the sake of uh, what's the name again? For the sake of best practice, because when you start working with others or when you start doing very big schematics and you have to do things according to best practices, you really need this advice. Okay, so just take it from me. So I just duplicate this and then I rename this rather than creating it all over again. Sorry. RxDO. Okay, and we have to bring it here. So duplicate these two. And just connect them. That's it. And this pin header is connected here. Okay, so it's 6:13. Next week we would wrap up on everything. We will bring in the other parts and we'll just connect them in. The other parts, we wouldn't stress this much. As I said, over here we're wiring the brain of our system. Let me delete this schematic. Okay. So in the brain, we have to do a lot of stuff and yeah, you check out Oku Electronics. So all you need to know is that this uses 5 volts and then these are the other two pins. So one pin connects to 5 volt, the other to ground, the others to we will figure that out next week, but you can use any of the pins here. Okay, the same for this one, the same for this one. Okay, next week we would quickly wrap up on this. We'll do everything we have to do, and then the next 2 weeks you can start with routing. Okay, but we are not closing right now. Why? Because we just want to make sure we have done no mistakes, no errors in our circuit. So you go to the electrical rules checker. Make sure errors is checked and warnings are checked. Else error is unchecked. You have 29, but it doesn't show. So now it's showing. Okay. So 29 errors, like 29 errors. Why 29 errors? Well, most of the errors are pin not connected. Pin not connected. In schematic design, if there are pins that it expects in a way that all the pins will be defined. Okay, let's say you create a variable and you don't use it. Sometimes your compiler will throw a warning at you that you've defined a variable but you've not used it. At least you have to specify or use it. If you know it, then delete it, right? So over here, it's either you connect it to something like this, or you use what we call the do not connect or no connect flags, which is here. Shortcut is Q. So I come here and I just press Q. Okay. And then this is now on the mouse. Now, this is a time to just teach you a shortcut. So we have to do all of these, right? Do we have to click all of them? No, we don't. If they are evenly spaced, that is 1, 2, 1, 2, you can simply click the first one, and then on your keyboard you press insert. Okay, so I've clicked the first one. It's there. Press insert, and then it's added throughout. Added, added, added. That is this is one shortcut I learned, and it really helped my life. It really helped my life because imagine you have a lot of pins. Look at these are a lot. Are you going to click on all of them? I doubt. So that's a nice shortcut. Click the first one and press insert. I couldn't have done it here because one would have come here, but we have connected something here. So you start from here and you press insert. So run ERC and we are down to 6 errors. We have, okay, this and this. Run ERC, 2 errors. Wow, reduced exponentially. We have just 2 errors now. Now, these errors are saying that power pin not driven by any output power pins. What does that mean? Simply means that we haven't brought in our voltage regulator to supply the voltage. Okay, so you could leave it like this because we would use a voltage regulator. But in some cases, some rare cases where you still use a voltage regulator, and let's say it's passing through a switch. Okay, so let me switch to this guy. So let's say it's actually a battery. Let's say you use the battery and you connected it. The error will go. The error will go. But when you suddenly place a switch symbol here and you connect this to your ESP32, the error will come again that input power pin is not driven because we have passed through a switch and the logical driving capability of the battery has been masked. And in such a case, you can ignore the error because you know that your schematic is correct. But for the sake of some people are tidy freaks or neat freaks, whatever you call them. I'm one of them. So I want no errors, 0 errors. So here is what I'll do. And this tool is in the power symbols. Come here. Let me delete this. Search for power flag. Sorry, search for power flag. Flag. Okay. Power flag. What does this do? It just gives the logical driving. I don't know how to explain it. It just says that okay, at this place we are driving power. So where would you connect it? You can rotate it and put it here and then here. And when you are done, come to your here. Run ERC 0 and so you are done. Okay. But then when we bring our voltage regulator in with no switch, you would have to take these off. You will get an error actually when you leave them here. So just know that when you bring in your voltage regulator and you are getting an error, it's because you've added this when there's a voltage regulator. Okay. So you can delete this power flag. Power flag. Okay. One more thing. In some circuits, what people would do is that they would rather bring in the power flag and put it somewhere here. Then they would connect them like this. I've seen people do this. I used to do this. Then I put it here at the corner, top corner here. If there's 5 volts, so I'll put 5 volts here and I'll put the power flag here. And it's the same as doing this. Which is better? Honestly, it depends on you. It really depends on you. If you want them all to be at one place, you want to see them logically, and if you have just one schematic, fine, you can do this. So let's delete this. Okay. So I think we can do this and it's fine. So you run your ERC again. and we have there are zero warnings. So we have done the ESP32. It would work. It would work except that there is no power supply to it. So if you were to supply power to it in its current state, you can flash it, you can program it, you can do serial print and do stuff. But because there's no sensors or actuators like the pump and um, the distance sensor, you can't use it for any real world thing. You can use it to, I think you can use it for Wi-Fi stuff because it has the Wi-Fi antenna. Question is, what would you transmit, right? So we are done over here. You'd want to save. Keyboard shortcut Control S. At the top right here, um, I know you can't really see, but if you are following at the top title bar, there's some asterisk there, meaning that it's not saved. Control S, the asterisk goes ends, and you've saved your work. Okay. All right. So we would continue next week. Any final words for me? Just continue, do your best. The sad thing about PCB design when you compare to programming is that you need money. You need money to see your results. If you are into web dev or Python or any of those stuff that you just need your PC, you can see everything. You can see your results on your screen, right? But well, the power just went out over here. Okay. Yes, let me quickly end. So once again, I know that PCB design is a skill that it's hard to really put your all into due to the cost factor. You do a design, the only way you can enjoy it is when you have it manufactured and then you buy the components and you solder it and then yeah, it's working. If you made a mistake, that's money wasted, you get it. So don't worry, you guys will be fine. So we will continue next week. Just continue, do your best, and I cannot recommend this YouTube channel enough. Fails Lab on YouTube. Just watch his videos. Sometimes they are hard to understand, especially for beginners. But for those who have some experience, you know what he's talking about. Those of you who have no experience, just hang in there. Soon you will get it, okay? Otherwise, you can use other channels on YouTube. You can search for KeyCard tutorials. There is this guy called Professor. He's a Ghanaian. He's one of the guys that I was using to start PCB design. He has some videos on YouTube. Just search for Prof. Let me search here. I think Eric Obin. Um, A. Yeah, a lot too. Okay, just Professor. Let me add PCB. You know what? When I find it, I will send the link to you. Okay. Because he's a Ghanaian and he doesn't really do a lot of videos or those high-end YouTube videos. It's the YouTube algorithm is finding it hard to find him. Yeah, that's the sad part of uh living in Ghana. But yeah, I'll find it and send it to you. That one too is a good starter course for PCB design. So it's 6:25 and we can close. So all the best to you guys, and I would see you next week. Bye.